So now let's take a look at a slightly more complicated problem from Module 9 for ME 270 Structural Dynamics. So in this problem here, we have a simple pendulum of length L and end mass M that pivots about a body of mass M, capital M here, that vibrates in the horizontal plane as shown in our figure below. Now they want us to use Lagrange's equations to determine the equations of motion of the system while making the assumption of small oscillations. So we can come down here to our given diagram for a simple pendulum attached to a translational mass. So we can see we have our capital M here for the mass of our cart here. So attached to that right there, we have our simple pendulum of length L and mass M, and mass M right there. And we can see that this position of the pendulum is given by our angle theta here relative to our vertical axis. You can also see that the cart is attached to a spring of constant K right there. And we have our distance of motion in the x direction to the right, positive there, where we're going to say that x is equal to q as we plug into Lagrange's equations. So our next step, now that we have all of this information here, is to come up with a plan of attack and do a little setup page to understand how we can use Lagrange's equations to determine these equations of motion for the system. So now that we've had a chance to read through the problem statement, see what they've given us with information within the wording of the problem and the given diagram, our next step is to create our setup page. So in our setup page here, we have our example, we have our length as L, our spring constant is K, end mass is lowercase m, and this pivots about a body of our mass, uppercase M. So we can see here's our uppercase M, our body of mass here. We can see our pendulum here pivots about that point there. Our length of our pendulum is given to us as the L. Here's the M, or the end mass here, our spring constant K, and you can see our x direction given right there, and our theta term for our angle relative to our vertical axis here. So from here, what we want to do before we start solving the problem is to figure out what key equations we're going to use and what methods we're going to use. So the two generalized coordinates will completely define the motion of our system here. So we have z1 using x direction here and z2 as theta as well. So here's our x and here's our theta term right there. So therefore there'll be two Lagrange's equations and there'll be two free body diagrams. So the two free body diagrams, one is going to be for the mass M and one is going to be for the pendulum. So we're going to do one for our mass M here, free body diagram, and a free body diagram for our pendulum as the second free body diagram. Now we're also going to have a kinetic energy equation that we're going to use and a potential energy equation we're going to use. And for these, we're going to say that our x here is equal to q. So our kinetic energy equation, the kinetic energy of our mass, capital M, is equal to 1/2 mq dot squared. And our potential energy, V sub m here, is equal to 1/2 kq squared. So let's start off with our mass M. We'll do out our free body diagram here. We can see here is our block for mass M right there. You can see we have our x dot going in the positive direction to the right and our k of x going off to our left direction over here. So that's a free body diagram for our mass, and we'll also have our free body diagram for our simple pendulum here. Now with the simple pendulum, we have this guy here, and what we want to do with this here is we have our resultant right here, but we need to break this down and do a little bit of trig and a little bit of geometry. So if we know that this angle here is our theta, we need to figure out a couple other things. So we can see here, okay, if this is our theta term here, we also have an opposite interior angle down here. If I draw up this dotted line here, that's our theta there. So from that, we can also determine between these two, our L theta dot and our x dot, components of our resultant here, that's a theta term here. So if that's a theta, then this opposite angle over here is a theta as well, which would make this angle right here beta, which is 180 minus this theta, because this whole thing is 180. 180 minus theta will give us just this portion right in there. Now we can also do a little bit more trig here, and we know the total length of this guy is L. So if we want to figure out, if this swings down here to this position, it's still length, it's still L, that doesn't change. But what is this length right here? So that's where we come over here, we can do out a little bit more geometry and a little bit more trig. We find out that this is L times 1 minus the cosine of theta for this distance right there. So how do we come up with that relationship that x is equal to L times 1 minus the cosine of theta? Well, a little bit of trig and geometry over here. We take a look at our simple pendulum here. So here it is with our length L down to the end mass here at this point, and then we're over here when it is completely vertical and straight down. This whole length here is still L. But if we're interested in this last little bit right here, that I'm just going to call our x term, well, then this top length here from there to there is going to be L minus our x term. So that's why we have our L minus x there. So look at this. We have our theta angle right here. Here's our adjacent, hypotenuse, and opposite. So recall that the cosine of our theta is adjacent over hypotenuse. So our adjacent is L minus x, and our hypotenuse is our L. So our cosine of theta is equal to our adjacent, or our L minus x, over our hypotenuse, or our L term right there. So then with this here, I look and I say I have an L over L and an x over L. I can separate these out, separate the fraction. We have a cosine of theta is equal to L over L minus our x over L. So L over L is simply 1, so we can reduce that down. The cosine of theta is equal to 1 minus x over L. So from here, I want to rearrange and solve this whole thing for x. So first thing I'm going to do is I'm going to take this minus x over L here, add it to both sides. When I do that there, I come over, add it to this side over here, our cosine. Now the cosine of theta plus x over L is equal to, all I'm left with on the right side is 1. So from this here, I still want to get x by itself here. So the next thing I'm going to do is subtract out the cosine of theta. So I subtract the cosine of theta from this side, and I subtract it over here on this side. So I have that x over L is equal to 1 minus the cosine of theta. Now I can multiply both sides by L. When I do that there, it eliminates the L here. So we have x is equal to L times 1 minus the cosine of theta, which gives us our answer that we saw on the previous slide. So as we continue our solution now, next thing we want to look at here is our kinetic energy. So recall our equation for kinetic energy, 1/2 mv squared. So for each of these things here, we have T is equal to 1/2 mx dot squared and 1/2 m r dot squared here. So we need to develop a relationship for the resultant velocity, our r dot, of mass m. Now this can be accomplished using our law of cosines. So if we recall for our law of cosines, what we have here now is we have this relationship here. Here's our triangle, like this here, okay? So angle A, our angle B, our angle C right there. And we have our side A, side B, and side C, just like this here. So this is our law of cosines, tells us that this is c squared minus a squared plus b squared minus 2ab times the cosine of c. We look back over here, here's our specific problem here, so we can say c squared, which in our case is our r dot squared there, is equal to a squared plus b squared, or x dot squared plus our L theta dot squared, minus 2 times ab, which is x dot L theta dot, times the cosine of c. Our c in this case here is our beta times the cosine of beta. So now we can plug in here, and we realize we've already found by doing a little bit of trig and geometry earlier that our beta is equal to 180 minus theta. So we can plug that in for cosine of beta is really the cosine of 180 minus theta, which is the same as saying the negative cosine of theta, to reduce and simplify a little bit here. So our cosine of beta within this relationship down here, we can replace with the negative cosine of theta. So we plug that in. What we end up with now is r dot squared is equal to x dot squared, L squared, theta dot squared, minus 2 times x dot L theta dot times the negative cosine of theta. So putting this in terms of our q dot now, instead of our x, this becomes r dot squared is equal to our q dot squared, when we replace our x with that, plus L squared plus theta dot squared plus 2q dot L theta dot times the cosine of theta. So now that we have a relationship for our r dot squared, we can go back to our equation for kinetic energy here, our T equation here from before. We have this relationship right here. And what we can do now is plug in for our relationship r dot squared. So we take that relationship we have here for our r dot, we plug in right here. So we end up with, for kinetic energy, is T is equal to 1/2 mq dot squared plus 1/2 m. Now we plug in our r value, our relationship right there, of q dot squared plus L squared theta dot squared plus 2 q dot L theta dot times the cosine of theta. Now for this here, what we're going to do is we're going to let our q1 equals q and our q2 is equal to theta. So when we do that and plug those back into this above equation here, we end up with is t is equal to 1/2 m q dot q1 dot from this relationship right here plus 1/2 m times our q1 dot squared plus L squared plus our q2 dot squared plus 2q1 dot plus LQ2 dot times the cosine of q2. So for the next step of our solution, what we want to take a look at is our potential energy term, our V. So recall a relationship for V here. V sub P is equal to mgl times our H value, where our H value here is 1 minus the cosine of theta. And we have our V sub m, which is equal to 1/2 kx squared, or our place replacing our x with a q, so we have 1/2 kq squared. Now total potential energy is going to be Vm plus our Vp, our mass and our pendulum. So plug these in together now, plugging in for our V sub P and our V sub m from the pendulum and the mass here. So our total potential energy, V, is equal to 1/2 kx squared plus mgl times 1 minus the cosine of theta. So we come down here and we can replace again our theta term and our q term with the relationships we saw on the previous slide there. So V is equal to 1/2 k q1 squared plus mgl times 1 minus the cosine of q2, and we replace our theta term there. Now we're going to call Lagrange's equation. So for Lagrange's equation, we have d over dt, the derivative with respect to time of our partial of our kinetic energy with respect to qi dot, minus the partial of t, our kinetic energy with respect to qi dot, plus our d over qi of our v, our potential energy, is equal to pi, where I is 1 and 2. So now we have equations for kinetic and potential energy. So for I equals 1, our kinetic energy T is equal to 1/2 m q1 dot squared plus 1/2 m times q1 dot squared plus our L squared q2 dot squared plus 2 q1 dot L q2 dot times the cosine of q2. So that's for our T, our kinetic energy. Now for our potential energy V, we have 1/2 k q1 squared plus mgl times 1 minus the cosine of q2, and our P is equal to 0. So next, let's look at the first term of Lagrange's equation. So this is a pretty long and involved equation here. We're going to do it term by term, solve them each separately, and we'll combine at the end once we've simplified. So we have the partial with respect to q1 dot of our kinetic energy T. So let's take a look at that there. So this is when we take our partial with respect to q1 dot, we have 2 times 1/2 times m times q1 dot plus mq1 dot plus m times lq2 dot times the cosine of q2, where 2 times 1/2 combines to be a 1, cancels out there. So then from that there, once we have the partial of t, the next thing we need to do is take the derivative of that partial with respect to time there. So we do that and take the derivative of that function up above with respect to t, and we end up with mq1 double dot plus mq1 double dot plus lowercase m L q2 double dot times the cosine of q2 minus m L q2 q dot 2 squared times the sine of q2. So you can see this is why we really want to break these up and do them term by term, because even the individual terms get very long and complicated. It's easy to drop a sign, drop a dot, lose a variable. So we got to be really careful and just do it term by term along the way. So now if we were to take the partial of our kinetic energy with respect to q1, this simply becomes 0, so that reduces and simplifies. And if we were to take the partial of our potential energy with respect to q1, this simply becomes k times our q1. So we're slowly getting all these terms figured out that we can plug back in. So we'll take these pieces and put them together in Lagrange's equation next. So we end up with here, we have m q1 double dot plus m q1 double dot plus lowercase m L q2 double dot times the cosine q2 minus our lowercase m L q2 dot squared sine q2 plus 0 plus kq1 is equal to 0. And again, even my handwriting gets a little messy, so we really do want to reference back and forth between our different pages and clearly label things, box things in. So what we're going to do here is I'm going to say, okay, I have a common M, capital M and lowercase m here with my Q1 dot, so I can pull my Q1 dot out there. And there's a couple other simplifications I can do along the way to end up with this relationship here. So a simplified, rearranged version of Lagrange's equation. So now, for small angles oscillations, we have the cosine of Q2 is equal to 1, the sine of Q2 is equal to 2, and Q2 dot squared goes to 0. So knowing those relationships for these small angles of oscillation, we can then put these back into the equation above to reduce and simplify even further. And we do that and plug these values back into this guy up here. We end up with a simplified version, capital M plus lowercase m times my Q1 double dot plus ML Q2 double dot plus KZ1 is equal to 0. So now we want to repeat that same process, but now for I is equal to 2. So for I is equal to 2, we do the same thing here. We recall back to our general form for Lagrange's equation over here, taking the derivative with respect to time, the partial with respect to our Q dot there, partial with respect to our Q's there. Same thing as before, but now our I's and our Q's are now 2, for my I is equal to 2 there when we plug into Lagrange's equation. We have our simplification up here, Q1 is equal to X, Q2 is equal to theta, cosine of theta is 1, sine of theta over here. So now we have all this information, and we can plug back in to Lagrange's equation that we end up with now here for I equals 2, ML Q2 double dot plus ML Q1 double dot times the cosine of Q2 minus M times L Q1 dot times Q2 times the sine of Q2 times MGL sine Q1 is equal to 0. We can reduce, simplify, rearrange, same as we did on the previous slide there. And then what we end up with down there when we plug in for the small oscillations, we end up with this relationship here, ML theta double dot plus MX double dot plus MG theta equals 0. So for I equals 1 and I equals 2, our equations of motion now become these right here. Look at this. We have capital M plus lower m, x double dot plus ML theta double dot plus KX equals 0. And then we have ML theta double dot plus MX double dot plus MG theta equals 0. So from this here, what we can do is let's just plug these into a matrix. So we end up with this matrix over here, relationship for this here, when we take these two equations, put them in matrix form.